Hi, we're Group Aries, and today we'll teach you how a helium neon laser works. Let's find out. How can we produce laser? For the production of laser, there are two main processes: simulated emission and population inversion. For the case of a helium neon laser, there are gases that are being used. Both are helium and neon. These gases are kept inside a container. So first, before we go on and discuss each process in detail, we need to know the ratio of helium to neon atoms in the container. So the ratio, we should know that for every 10 helium atoms in the gas container, there is one neon atom that's floating. So this gives us a ratio of 10 to 1.
Atoms can be in distinct states, ground states, or other different distinct levels of energies. This is due to the electrons being excited by something. At the starting of the production of a laser, electricity is given to the helium gas atoms. They will move to a higher energy state of 20.6 electron volts. Then they collide with the neon atoms. Their energy is transferred to the neon atoms and they go back to their normal ground state, which means that they lost their excitement. The neon atoms then move to a higher state of energy of 20.66 electron volts. When atoms move to a higher state, they then drop to a lower state and emit a photon of the same difference in the energies between the states. Neon emits a photon when it drops to 18.7 electron volts, which has a wavelength of 632.8 nanometers, which means it is red in color in our eyes.
For this process of producing photons, population inversion takes place, whereby neon atoms shift from the ground state to a higher energy state. And by population inversion, we mean that there are less neon atoms present in the ground state and more neon atoms present in a higher energy state. This process will allow simulated emission to take place, as we will explain later in this video.
Photon with 623.8 nanometers causes stimulated emission. The photon passes by the neon atoms that have energy of 20.66 electron volts and stimulates these neon atoms to release photon that has the same wavelength as the initial photon. Like a marching band, these photons move in the same speed and frequency and are in phase. They bounce on mirrors on both ends of the laser tube. When they travel the opposite way, they stimulate even more emission of photons. The mirror at the end of the tube is 99% reflective and 1% transparent, so 1% of the photon will travel out there. This is our laser light we see.